Uh, let's talk about section 1.3, which is titled More on Functions. So the first section is functions, second section, I guess, revenge of functions, now more on functions. These three are introductory lectures where we talk about functions in general. So far we know that a function is a rule, as I have foreseen. See? It's a big issue.
Assign to each x in the domain a unique y in the range.
All right, so we know all the letters. Excellent. So we know what the function is. We know hopefully what it means. We know domain. We know range. We know how to find x and y intercepts by setting either x to 0 or y to 0. We know what the meaning of the interval is, what the point is. We know how to graph using the table of values, which means that you pick x values and then you compute y values. You have ordered pairs which you plot and then connect the dots. So you know all of that stuff so far. The major part was computing the function. So knowing that notation, I'll write it one more time just in case. So we said that we are going to now use y equals f of x as a notation. So what you used to write as y equals 2x plus 3, now you're going to write it as f of x equals 2x plus 3, because you are emphasizing that this x is independent variable, and it is this x that will be replaced by numbers, which would be function values. So now if you want to compute f at 5, you will have simply 2 times 5 plus 3, which is 13. Now the function could be anything else. We said the square roots, absolute value, trigonometry, which is next semester, and so on. Many functions out there. There's actually a book that has 2,500 pages, which is called Mathematical Functions, where polynomials will take a half of one page. By Abramovich. So you can take a look at that and just imagine the vast amount of mathematical functions. We're going to cover 8. That's going to take good 4 pages of that book. All right. So what else do we need to know? Now we are going to look at certain properties. We know how to graph functions. So if it's a linear, you know it's a y-intercept and then count the slope. But if it's anything else, you know how to compute the values and plot those. We want to now talk more about the graphs themselves and analyze the graphs, because most of the work when you are in a field, working at the company, whatever, you will be interpreting graphs, and in some cases you might have to make quick decisions and quick choices looking at those graphs. So I mentioned last time that if you have, let's say, a graph maybe that looks like this, we are going to have the point here, which is the highest point on this piece. Now there are points that are higher on this side, but this over here is going to be a local maximum, which happens at some point. Let's call that point A. Now if I plug in A into the function, the answer for it would be f of A. So the coordinates of these points are A, f of A. That's mathematical notation. A, f of A. Which means that if you choose A that is 3, then you have f of 3 to compute, and so on. Over here somewhere, we're going to have the lowest point, known as minimum. Let's say that happens at B. So this one will be B, f of B, because B is the value that I'm plugging into the function and computing. So I have these two. Now we can also find the x-intercept, y-intercept, and all other stuff that we did last time. Now what I am interested in with this graph are the concepts of increasing and decreasing as a function. So we can see that as we are, because we read from left to right, as we observe the graph from left to right, you see that as you go from negative infinity on x-axis all the way to a, so we are technically looking at this part of the x-axis, you will see that the function is increasing on that interval. So we would say increasing negative infinity to a. And we do not include a because, as I said last time, we cannot judge increase, decrease looking at one point. So one point, single point, is never important, so we don't have to include that a. Then we have the blue part here, which goes a to b, and that's decreasing, which is between a and b in this particular example. And I'm going to go back to red because it's again increasing. So increasing from b to positive infinity. You can put plus infinity, you can just put infinity. And as you can see, we never used any y values. Maybe you want to write that as a little note on the side. Intervals are always given from x to x, 2x values. I'll just put x1 comma x2. This is one of the problems in mathematics. I'll write this on the whiteboard. We have same notation for different concepts because there's just a lot of mathematical concepts out there because mathematics is underlining everything that exists in the galaxy. So it covers the business and everything. And there's just not enough symbols for us to represent everything. So these unfortunate situations will happen, and we will see more and more of them as we go through the class. You see this point over here? Let's call this point 2, 3. You know it's a point 2, 3. This is number 2. This is number 3 on the y-axis, and you know how to find point 2, 3 on the coordinate system there. Now I'm going to go here, and I'm going to say 2, 3. So there's number 1, 2, 3, 4, and I'm going to shade this little interval, and this interval here is also known as 2, 3, open interval. Absolutely same notation, much different interpretation and meaning. This is a point where you have x comma y, and this is the interval which has x comma x. So this is, and the concept goes like this. When you say that you're going to be in class from 3 to 5. That's this. It's a notation because these two are the same dimension, time. So 3 to 5 means 3 p.m. to 5 p.m. Both of those numbers represent the same quantity, same quantity, which is time. So it's the same variable, so x comma x. You're in class 3 to 5. So that's interval. The other one is a point where you pay, I don't know, $2 to buy 3 pencils, right? So these are different units, and that's why you have x and a y, different dimensions, so different units. So these kind of issues will be constantly popping up in mathematics from now on, and it is from the context and from how much knowledge you accumulated that you will recognize which one is the one we're talking about. Whether it's a point, so when you see 2, 3, you say, is that a point or an interval? So now, the question that we are covering in this class is, what are the intervals of increase and decrease? And you say, okay, intervals. That means that I have to provide 2x values, so the function will be rising from negative infinity up to a, and then decreasing between a and b, and then increasing again from b to infinity. So you are strictly providing these. Now, if I ask you where is the maximum, you will say it's at a f of a. Now, those are x and a y. It's the x coordinate and it's the y coordinate. So that's the point in space. So that's the difference. And if you don't understand this, you might answer the question wrong when I say, oh, it's decreasing, and then you list this and this. Technically, that's right, but it's not an interval. You gave me 2 points. the interval is a to b, x comma x, and you are listing point comma point, which is not a proper answer. So you have to be really concerned with notation, and you actually have to study. You have to learn the vocabulary. You have to learn theorems and definitions. So all of this stuff eventually makes sense. So that takes care of the increasing and decreasing part. Now we also can have a part where the function is constant, in which case you will just write constant piece. So we can, let's take a look at another case. So let's say we have what we in mathematics call piecewise function, which means it's going to have multiple functions within each of the intervals. So let's say you have a linear piece, and then you have quadratic piece, and you have something like this, let's say, and then I don't know, it's good, it doesn't matter. That does something. So if I am to use values here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wow, what are the chances that I randomly just went 4 units each one? Wow. All right, fine. So now, interval of increase, we start at negative infinity, and then it's increasing to 4, and then we say union 4 to 8. So there is at 4 there is this jump, but the function is still rising. But you can't say in one shot that it's increasing from negative infinity all the way to 8 on the x-axis, because you can see that at 4 it dipped down, right? So this piece is increasing up to 4, and this piece is increasing, and then we unite them. Yes? That's why this one is open and this one is closed. So this one does not contain a y value, and this one does. So the point for 4 is actually here, not there at all. Awesome question. And that's actually, so now I know that you studied the definition of a function, because you know that 1x cannot give 2 other y's. So those are some good points. So see, it's already, he's already passing. Yes?
And always is increasing, decreasing, constant. They're always in the, they're not
parentheses, yes.
Parentheses,
yes,
they're
parentheses,
always.
because
Okay.
you see, and one more time, we have to interrupt at 4 because you can see clearly a dip over here, but then that's happening only at one point, and we can't consider increase, decrease at the point at all. Then we have a constant piece from 8 to 12. And then we have a decrease 12 to positive infinity. And I hope that you understand, guys, that these are intervals. So every single value that I placed in here is an x value. So the function is increasing between 4 and 8 on x. You see that the piece above between 4 and 8 is going up. The piece between 8 and 12 is constant, straight. The piece between 12 and infinity is decreasing. So we provide intervals on x-axis, and then we get that stuff. Yes?
Why would it be negative infinity?
Negative infinity is...
Or decreasing?
No, the positive infinity is on this side, positive infinity. X value positive infinity.
Okay.
All right, so let's take a look at how some of the people make money off of what you just learned, right? So what I'm going to do is I'm just going to take a look at the stock market real quick. So we are switching. This is not captured on stream because it's going from the main computer, so you can't see. But I typed in Apple stock, right? And you see that Apple stock is valued at 105.50 cents, right? So you're looking at this stock, and this is 1 year. So from September 15 to September 16. And you see how this is a function, right? Because at any time, at any day, you have a particular y value, which is how much the stock is worth. So let's say you have 10,000 shares. 10,000 shares times 100 is how much? How much you have invested? If you have 10,000 shares, it's 105 per share. You have 10,000 shares. 10,000 shares. Next one?
105,000.
It's $1 million. Okay, good. So I have 1 million invested, right? You have 10,000 shares times 100, you get 2 zeros. Right? 10,000 has 4 zeros, and then you add another 2, 6 zeros, 6 zeros, 1 million. So if you have 10,000 shares, the amount of money you have invested is $1 million. But let's forget about that. Let's just think about you having 10,000 invested, and the stock drops $1. How much did you lose? $10,000. If it drops $2 per share, how much do you lose? $20,000. If it goes up by $5, how much did you make?
50,000.
You made 50,000, exactly. So being an investor is a tricky business because you have to follow a lot of news and a lot of media and a lot of trends, right? And see, and then you see, look at that. That's $2.82. What does it mean? If you have 10,000 shares, you just lost almost $30,000, right?
But why did the started at 49 and now it's 53?
The market's still open.
Yeah, market is open to 4. This is yesterday. Since yesterday's closing, the cap. So since yesterday till today, this is how much you lost. No one should like any of them, but let's just put. So looking at this stock, right? You know how much it's going to fluctuate. So you have to make quick decisions off of a graph. And this is the part where increasing and decreasing and recognizing it. And also, which is going to be our section 1.5, how fast it dips, how slow it goes down or up. You can see that this is much faster going down than this part going up, right? So you have all of these, and you obviously link it to the new product, all, you know, and then there's nothing new, and then, you know, it goes up and down. So this is a year of data. You can keep switching between 3 months, 5 years, and so on. So last 3 months. This is how it looks like for last 3 months. Last month. Last 5 days. And today. So on a daily basis, it's pretty flat, right? But that's when you really zoom in. But the market started, right? And so far they lost $2.76 per share for today. It's closing in 30 minutes, so most likely that's it for today, right? It's going to be a loss. So if you have 10,000 shares there, you're probably losing $30,000 today. It might bounce up tomorrow, might not, might dip even further. So what we cover today, this is exactly what it is. You will look at this for the entire domain, 9 a.m. to 4 p.m., and you will say the function is decreasing for the entire domain. Where if you pick a different set, you will be able to distinguish between Here is the increase. Now you try to smooth this out. You're not going to, be concerned with every little hiccup here. You will smooth this out. One line, one line, one line, right? Wherever there is a trend of following, right? Because this, this single dip that was there for like 2 days, who cares, right? Because on average, for for the entire 2 months, it's going to be a nice straight going up. So people who are dealing with these things, you have brokers who are managing other people's accounts. So your job is to manage someone else's account because that person is completely math illiterate. Like, take any of the stars. You think they actually know any of it? Hell no. They're paying big money for someone who actually learned this in a class like this. So that person is managing their $150 million portfolio, right? That is for, I don't know, Apple stock or whatever. And that person is going to look at these increase, decrease, and say, oh, buy, sell. And make those split second decisions for whether to buy, whether to sell, and go on because, again, looking and predicting and watching the news and following trends and so on, understanding the product and so on. I guarantee you go into a market without knowledge of this mathematics that we're covering in Precalculus 1, and without following news and following things, you're going to waste whatever you put in like this immediately. Because you're just going, and it's not going to be, oh, those are rookie mistakes. There are no rookie mistakes. It's just a fatal mistake, and that's it, you're done. So buying the wrong spot, buy at the wrong time, sell at the wrong time, and it quickly disappears. So there's another one. It's a money market with foreign currencies and so on. Can do that kind of trading as well. They ask you to start off with $10,000 investment. So the interesting thing is they say, here we're going to give you fake money. You have our system. You go and you play with it. You buy, sell. So it's actually, they give you the money to play with. It's not real money. It's virtual money, but it's on the real server. And then you kind of try to learn how the software goes. And then when you invest a real 10,000, then it becomes like, then it's stress, right? And then you most of the time, if you don't know the concepts that we're covering in this class, then obviously it becomes an issue. So technically, guys, when you are looking at what we do in class, there is going to be an equivalent somewhere in the everyday, day-to-day business out there for you to apply this. Otherwise, no one would bother to come up with these concepts and things, right? So that's that piece. So that's the increase and decrease part of the lecture. Now we're going to talk about mathematical symmetry. We're going to talk about two different types we have. We're going to distinguish between even functions and odd functions. And this will really test whether you study that or not at all, because you might understand this or not. Let's see. So formula or expression that checks for odd function is given as f of negative x is the same as negative f of x. So this is the statement. So function is odd if this is true. Function is odd if this is true. And this is your formula. So now you need to know how to apply this to check if the function is odd. It's going to involve plugging in and doing a lot of stuff. So let's say, check if f of x equals to, I don't know, 2x cubed minus x is odd. So check if this is odd function. And this is where you go and you say, well, I know the function notation and I know what this means, so let me create f of minus x first. Now, if I compare f of minus x and f of x, I see that they are different by just having a minus sign in front of each x I have. So I will replace every x with negative x. So this is what the notation of a function tells us to do. replace every x with negative x. And we are essentially creating the left side of our formula up there. So now you apply algebra. This is going to become, when you apply the cube, so that's going to be negative x times negative x times negative x, which is negative x cubed. So we have negative 2x cubed, and minus gives us plus, and we get plus x. So the left-hand side of our formula is negative 2x cubed plus x. Now we want to compute the right side. Right side is going to be a little bit easier because you apply minus to the entire function. So now, distribute the minus, and we get negative 2x cubed plus x. So the formula says, so you have, let me just write here, so this is the left-hand side and the right-hand side. Left-hand side and right-hand side, those short notations. So the formula up there says that if these are the same, then function is odd. And they are the same. Since f of minus x is equal to minus f of x, function is odd. Now we'll go into graphical representation soon. I want to also define the even through the same thing. So let's take a look at the even. Formula for even is that f of negative x is the same as f of x. And let's go with the example. Check if f of x equals to x to the 4 plus 2x squared minus 8 is even. Well, we need to create f of minus x. What am I supposed to do? Yes?
Replace all of the x's with negative x.
Very good. We replace every x with a negative x. Negative x to the 4th plus 2 times negative x squared, and then minus 8 stays as minus 8. Use the algebra skills. So negative times negative times negative times negative is positive. Very good. So x to the 4th. And then plus 2x squared, and then minus 8. So that's the left-hand side. The right-hand side, well, just don't touch it. You see the up there, it just says f of x, which is the original f of x you were given. They're the same, right? Since f of minus x is equal to f of x, the function is even. And those are the rules. So you must memorize, you must learn these two rules. One for odd, which says that f of minus x is minus f of x, and one for even states that f of minus x is f of x itself. So these are the two rules, two formulas that you need to know. Now this concept is going to be there in your Precalc too. You will learn that sine is odd function, tangent is odd function, cosine is even, secant x is even. You will have those there. And then you're going to move into Calculus 1 eventually, where you're going to have in Chapter 5 certain formulas which state that if function is even and the integral is on a symmetric interval, solution is so-so, and so on. So many simplifications later on in life. even further looking into Fourier transforms and stuff, you are going to have these concepts come back. And this is the one thing that I promised you on the first day. Every single concept from this class, from day one until we have the final exam, will come back. Every single one of them. And whatever you forget from this class will eventually hunt you down in one of the future classes. Most of the stuff is going to be there in Calc 1. Whole bunch of trig in Calc 2. Everything back in Calc 3, differential equations. Because future classes will use these things as either a simple trick or a simple step. Now they're full problems because you are learning it for the first time. But down the line, they become a little piece of a puzzle that you do. Should we check one of the DiffyQ problems? Yeah? Let me see if I can dig it up. There we go. Differential equations. That's still same problem. There's the solution. Yeah, this is one problem. It starts over here, problem 10 from the textbook. And there you go. It's fun. So, yeah, I know. But guys, you have to understand that this is not something that you walk in. This is not something you walk in and you learn from scratch. You have to understand that you build up to this point from today. And every concept that you skip today in this class till the end of the semester, you will not be able to pick up some of the things to go through into the concepts needed to solve this. So this is why I'm constantly stressing you're not learning precalculus to pass it. Precalculus has the name, precalculus. And the calculus is before differential equations. So you are looking 4 courses ahead. This is 4 courses ahead. Rafael sits in this course right now and loves it. What do you mean? All right, we'll have to switch our RSI for the class. But the idea is I am really looking for you guys to realize that these concepts now get upgraded. And if you don't know the base, you can't upgrade it. Or to upgrade it, you will have to sit and relearn it at that time. So by the time you're in differential equations, you'll be learning, if you want to learn that problem you saw from scratch, you actually have to sit down for 10, 15 hours to pick up all of the little pieces from the past to do that thing, right? So that's why now is the time to spend it and invest, which is the reason why we don't have too many people in math programs, because you don't invest that kind of, you know what's the percentage of Calc 2 on campus? Of all student body? 1%. I always welcome my Calc 2 students on the first day. I welcome them to 1% of population. And differential Raphael belongs to 0.5%. That's the differential equation. 0.5%. So think about those opportunities for employment and transfers and so on, where either 1% or 0.5% is your competition. Right? So you're talking about 10 to 12 sections of Precalculus 1, right? Which is whatever in terms of, so let's see. So you guys are probably about 6.5% of students at RVCC, believe it or not. Uh-huh. Yeah, well, the college is business administration. Yeah. You want to be 1%, you go into Calc 2. 1%. Calc 3, 0.5%. And that is your competition later on. This is why you sit in a class like this and you actually learn, not mess around. And I told you this class at Rutgers is $2,000. So 2,000. Yeah, it cost you here with all the fees and stuff probably 750. So yeah. So pay attention. Let's talk about symmetry. One step at a time. Should start calling you 6%. All right. So what do you have with these even and odd functions? Well, first of all, I went through the boring part, which is there is this formula that you can memorize, and then you grind through that formula, and then if the formula works out, function is either even or odd. If the formula doesn't work out, any of them, then the function could be neither as well. So functions could be even, odd, or none of those. One of the three states. And then now we would like to see what are these physical ramifications. What is what is the graph doing for it? So if I go and I graph y equals x, y equals x is odd. How do I know that? Well, I check the formulas. For odd, I check f of minus x is minus f of x. Is it? Well, minus x is equal to minus x, that's true, so it's odd. If you try to check for even, you will see that it doesn't work. F of minus x needs to be the same as f of x, so f of minus x is minus x, and f of x itself is x. That's not true, so not even. But it is odd. It can't be both at the same time, so once you figure out it's one, it's not the other. So I have y equals x. Now what is the graph of y equals x? Anyone remembers that one? Straight line through origin, good. At 45 degrees, right? Right. So we have straight line. For odd functions, we say there is the symmetry through the origin. Now I'll have to come up with more functions so you can see it, but it's symmetric to the origin, which means that the piece on the left of the 0, 0 and a piece on the right of the 0, 0 must look the same if they are reflected through the origin. Now let me go and do another example for this one because these are hard to see. So y equals x cubed is also odd. If you don't believe me, you will write those formulas and you will see. If anyone knows how cube formula looks like this. Now we're going to have a whole chapter, chapter 2, where we will learn how to graph every single one of these. So this is your x cubed graph. Again, symmetric on 0, 0. Because if you look, right, this point corresponds there, this point corresponds there, this point corresponds there. So every single line that I am able to connect goes through 0, 0. And it has its pair. So if this is 1, 1 on this side, then you have 1, 1, or negative 1 on the other. So you just put both negative signs. So we have all of those. So that's the meaning of the oddness of a function. It's symmetric through the origin. How about even? Well, y equals x squared is an even function, and that one is symmetric on the y-axis. So odd functions are symmetric through origin, and even functions are symmetric on the y-axis. Now these concepts will be used later on. Here is the preview of your Precalculus 2. Cosine x, that's your Precalc 2 function. You will see that the cosine x does this in its original form, but it also has, it's a wave that goes forever like this. But you see it's symmetric on the y-axis. So symmetry is observed at all times there. doing the same thing forever. Gonna do that. So that is what a symmetry means. And then these concepts of even and odd will be back in every math class you ever take from this point on, as everything else from chapter 1 will be back every single time. So those are the concepts of even and odd. And I think we covered everything. Oh no, we have the difference quotient thing. So let me just. See you next week, huh? Okay. So two more parts for this. I almost forgot, I did mention earlier, piecewise functions. Piecewise functions are frequent in calculus courses, and we need to know how to represent a situation where the function changes from part of the domain to part of the domain. And the special type of these functions is called a step function, and the most famous example of a step function would be the tax brackets for tax collection, obviously. So let's take a look at first of these step functions. So what are the step functions? No, step function, sorry. The piecewise function as the general concept, and then step function as a special example. So we start first by understanding piecewise functions. I already had the example earlier. I'm going to scroll to show it. So this is a perfect example of the piecewise function. The piece from negative infinity to 4 is a linear piece, and it has its formula. Then you have a piece from 4 to 8, which is a quadratic piece, some kind of x squared. And then you have the constant piece, let's say y equals 7, or whatever the value is. That's going to be constant between 8 and 12. And then you have another linear decreasing function, 12 to infinity. So there are 4 different functions together. They're not overlapping. They're not on top of each other. They're to the side. So you can see and find intervals on which that function lives. So the entire domain for the function is from negative infinity to positive infinity, but you chop it up into 4 different regions because each one of those regions is housing its own function. So now, piecewise functions are going to say, let's just work on one. It has this big brace, and let's say you have x plus 1, let's say you have x squared, and then maybe let's do a third piece. I don't know, what should we use for the third piece? How about square root of x minus 5? All right. Let's go that the first one is on the domain negative infinity to, I don't know, to 1. And then the second one is on 1 to 5. And then this one is on 5 to infinity. So these are the respective domains. Now I'm also going to write them in a different way. X, you know what? Let me include some of these. Let's go in the middle one over here and put these guys in the middle. You don't have to, but let's just make them somewhere included. So it's going to be x less than 1. This is where x is stuck in between 1 and 5. And this is all x is bigger than 5. And observe the use of parentheses and brackets and conjunction with less than equal to on the other side. So you see whatever is the parentheses just less than, whatever is less than equal to, it was a bracket. So those are, again, two different notations for the same thing. And just use, carefully. So I can present these domains in any of the two ways, depending on which book you read. So let's graph this. Now, one thing is your calculator ain't going to do this. So you need to know how to do it. Even if you had your calculator on the exam, you would not be able to do it to graph something like this. X plus 1. Well, that's a linear line, right? We know. So the y-intercept is 1. And then slope is 1 over 1 in front of x. So it's a 45-degree line that goes forever up through 1, right? It goes like this forever. But then you say, okay, hold on. I get to erase now the part that it's after 1. Because at x equals to 1, this function stops to exist. This function is only available between a negative infinity and 1. So now I have to take my eraser, and I have to erase everything after 1. Because function doesn't live on that side. And I will place the open circle here at the end, because I had open interval, and open interval means does not include the point. Now I need to graph x squared. All right, I can graph x squared. I know it goes through 1, 1, and then it goes through 2, 4. So it looks like this, right? That's how x squared looks like. But you're going to say, hold on. I am only allowed to have x squared to the right of 1. So I have to erase this part of the line, because that's already taken with a linear. And I also have to erase anything in between 0 and 1, right there. I have to erase all of that. So this part is supposed to be slightly curved, right? It's not flat, it's a curved, it's a part of parabola, and it does going to have this hole over here. Now the unfortunate thing is that this is not drawn to scale, so this one over here will be at 25 height, and this part over here has to be number 5, because that's where it ends. And this is where the square root x minus 5 begins, which looks like this. It's exaggerated. So open circle, and then the square root. So now let's take a look together at all of the pieces. Piecewise function. The word pieces is there. It's not piecewise function. It's piecewise function. So we have 1, 2, 3 different pieces. They can never stack on top of each other, because that would immediately ruin idea of a function, right? You can never have two closed circles, one above the other, because that would also ruin function definition. So all of the pieces have to be to the side of each other. Where they belong, it will always be given to you in these portions of the domain. So this piece of a function, the first piece, is going to be on the interval -1 to 1, sorry, minus infinity to 1, so minus infinity all the way to 1. That's the linear piece. With the arrow here, it's going to go forever to infinity. Next piece is between 1 and 5. So 1 and 5 is the next piece, is x squared. So you will draw the x squared, because you know that's a u-shaped function. And then you will erase everything that is already taken by the linear, because if you draw another piece, then the vertical line has to fail there. That's not good. So we erase everything to the left of 1, because this says x squared only lives between 1 and 5. So if you are to make a tube, right, like this, forever, that tube would be where x squared is allowed to live. And then after 5, forever, you will have this function, which is a square root function. Now, this -5 shifts the whole thing to the right. 5 units, we'll deal with that later. So this is your general case of a piecewise function. How evil could these be? Well, the answer to that is, for the first time now, we're going to learn the difference between difficult and annoying. Okay? Things are difficult when you don't learn them, you don't know them, and you might have to work hard to catch up. Then things get difficult. If you know the concept of piecewise function, if you spend some time on figuring out the title that says piece, okay, pieces, and then you listen to what I said 15 times already, that each piece lives on its own domain, they never stack on top of each other. If you know all of these things, then the question can never be hard ever again. It's just the level of how annoying the question gets to be. What are these? Am I going to put linear and quadratic, or am I going to put some exponential stuff later on and things like that? So the question after this point becomes how annoying the problems are. Now, do we need this? And the answer is, hell yes, we need it. Because in engineering, you want to produce a particular piece, spacecraft or whatever that you're making. That's not just going to be a block, all right? That it's all 6 sides are parallel, everything's perfect, right? And just here you go, because things don't work that way, right? You're going to have curves on cars and things like that. You're going to make that bottle. I promise I'll. So if you look at this bottle, guys, look at these curves right here. The functions that the formulas that you have seen when I turned the whole system on was actually how to make this bottle using, and how to calculate the volume of the bottle using mathematical functions. Now you saw that crazy function. That's not going to be one function. It's going to be all of these piecewise functions. And you have to integrate that because it was within the integral. That was Calc 2. So again, you are learning now how to graph the basic piece. So you might actually model something like that. And then in Calc 2, you're going to upgrade that. You put the integral sign in here. And you say, aha, now I know how to find the volume of that crazy bottle. Because you really don't want to be working at a company where you say you're going to sell 16 ounces of fluid in that thing, right? And then someone who knows Calc 2 runs back your functions over there, finds out that you actually have 15.3 ounces, right? Which means you've been cheating on market for a long time, and you would sue your butt for a lot of money, all right? So you have to worry about things like that. And as I said, everything we do in class does have its what do you call it? Application in engineering and everywhere else. It's just your job to find it, where it fits, how it fits, and 100% of this, again, recycled in every following course you take. 100% of it. Next, let's talk about a special case of piecewise function called step function. And we can immediately look at that step function as our tax brackets. So if I am to look up tax brackets, I'm going to again bring it up so it's not going to show up on stream, but catch up what I'm talking about. So here we go with the PC. So what you have here, I just typed in Google tax brackets 2016. This is the first image that popped up. I'm really not checking the source, so numbers might be wrong. But yeah, you get the idea. So if you make, let's go with the single fillers. If you make up to $9,275, you'll be taxed 10%, which means that you technically will be paying in taxes $927.50. So that's how much you will be paying in taxes if you made this much money. If you make $1 more, you are in a 15% bracket, and the 15% bracket of whatever you make in this range. So you guys can see that this is your y-axis here, which is all these percents of how much you will pay because you made X amount of dollars in a year. And you are going to fall somewhere on this chart because it goes to infinity. You see that the 400,000 plus, right? So that covers Gates and Musk and these guys. So it goes from 0 to infinity. So you will fall somewhere. And each one of these, this is number 10, number 15, number 25, they're all constants. So now we're going to draw, looking at the data, we are going to draw the piecewise function. And once we see how it looks like, you will understand why it's called a step function. So let's take a look. I draw a little bit larger graph because we have values to work with. So this is the percent, and this is money. %, 20%, 30%, 40%, 50%. So the largest number, I don't need 50%. The largest percent is 39.6. So that's technically 40%. I have no clue where they come up with these numbers. Like, all of the percents are whole integer numbers, and then all of a sudden 39.6%. Why? Call it 40. All right. So now what we have here, let's say that this is 10K, 20K, 30K, so every 2 squares I'm using. This is not going to fit everything, obviously. This is actually terrible because it's not going to fit almost anything. 90, 100. Yeah, I need to go all the way 190. Ain't gonna happen. I'm going to introduce a little cut in the graph. Call this 190K, just cheat. When you have these little squiggles like that, that means that the piece of the graph is missing, but you're not, and the function should behave the same through that piece. All right. So 10%, guys. We go up to 9K. Then between 9,000 and 37.5, so 9,000 and 37.5, we are at 15%. 27.5. There we go. Then we have 25% from 37,000 to 91,150. And then after that, there is a 3% jump to 28, which is right here, right around the corner. And in our case, that's where I have to stop. Well, actually, no, I have 190. $190. and then at 190 up to 4,000, so at 33%. So 33% is right here. I'm just going to put this, but there's another one after that, which is at 35% and then at 39. Looks like stairs, right? Because we know that each step is flat. So step function, right? Looks like steps. Looking at it sideways. It's a piecewise function. Piecewise function because there's a piece number 1, piece number 2, piece number 3, piece number 4, piece number 5. Each one of those lives on its own part of the domain. They never stack on top of each other because that would ruin the definition of a function. And this particular kind, which only consists of horizontal lines, is called a step function because it looks like steps looking from the side. Very simple. So when you learn all of that vocabulary, and when you just stop and think about it for a little bit, those concepts should sink in. So that when you see them, not if, when you see them in Calc 1, you actually can do stuff with those. Cool. That's the piecewise functions. And the last concept that we are covering is going to be the difference quotient. All right. Difference quotient. So for difference, this is the last thing in 1.3. So what's the difference quotient? Difference quotient is going to be a formula which you are memorizing now. You are going to learn how to compute and simplify and use that formula. The purpose of that formula is unveiled in Calculus 1. And I will tell you what it is actually here, and I will even write it down. But you guys will not get to use it in its full glory, I'd say, because it's a Calculus 1 concept. But what we are covering here at this point is Precalculus, which is combining functions together. So what's the difference quotient? It is a formula that looks like this. F. What happened? I know what I'm doing actually. Okay. F of x plus h minus f of x divided by h. So this is it. So in Precalculus 1, of course you're in right now, this is just going to be a nuisance calculation. But once you go into Calc 1, it becomes the central idea of Calculus 1. So learn it now. Do yourself a favor. Let's do this. So compute difference quotient. So this DQ, it's not Dairy Queen, it's difference quotient in my case. So difference quotient for f of x equals to, let's just start simple, x plus 5, that's it. Okay. So you are looking at your f of x, and you can recognize that the formula has vanilla f of x, right? That's the minus f of x piece. So that will be a good cut and paste. But we also have f of x plus h. What do you think we should do there? Plug in x plus 5 instead of, yes. Okay. So I always do this because it makes you understand it better. If I have f of x is equal to x plus 5, f of 3 is going to be 3 plus 5, f of a is going to be a plus 5, and f of a flower is going to be a flower plus 5. So when you get all of these, it should be immediately common sense that this happens. So you always, in a function notation, are replacing entire x by entire whatever the hell you're plugging in. So this is the function in its original state. And I'm telling you between these two notation, replace every x with 3, and you go replace every x with 3. With this instruction here, I'm telling you replace every x with a, so you did replace every x with a. Flower, or x plus h, or whatever else you can come up with, which pretty soon in this chapter, we will be replacing this x with an entire function for something that we will call function composition, and you will have f of g of x, where you take the entire new function and plug it inside this function, and you have function inside a function. Now that sounds so scary and so foreign, but as soon as you realize that you have pens which have function, you put a wallet in your pocket, which also has a function, and there is a function inside a function. Very simple. Or you have the book bag, and you put something in, put the wallet in a book bag, so it's a bag has a function, wallet has a function, you plug one into another, and there you go, right? So all of these concepts, guys, work out there. You just have to find them where and how. So now, by looking at what I wrote over there, you see that this piece becomes x plus h plus 5 minus x plus 5 divided by h, and then you simplify the algebra. So what I like to do is I like to say, okay, first I create the f of x plus h piece, which would be replace x with x plus h, which when you get rid of the parentheses, looks like this. And now I can compile the difference quotient. If you want to call it difference quotient equals, go ahead. So this piece is x plus h plus 5 minus x plus 5. Don't forget the parentheses, because you have to subtract the entire function, divided by h. When you get rid of the parentheses, you see that x cancels x, 5 cancels 5, you get h over h, and the answer is 1. So that was the simplest example that we have. Let's take a look at a more spicy example. So compute difference quotient for f of x equals to x squared minus 2x plus 3. So who can tell me what is the f of x plus h now? Yes.
X squared plus
So x plus h squared?
x plus
Well, we'll expand it later.
okay.
So we do step by step.
Minus 2 x plus 8.
Nice. And then we just have plus 3 because nothing happens there. So please meditate on this. Every x in original f of x is replaced with x plus h now. So the shell of the function is the same. You have something squared minus 2 times something plus 3. Something squared minus 2 times something plus 3. Same. We replaced x with x plus h, so there it is, x plus h, x plus h. Now you expand all of this and you add like terms. What's the expansion for x plus h squared? Yes? X plus 2? Yes, 2hx plus h squared. Minus 2x, minus 2h when you distribute, and then plus 3. Don't forget the middle term. Okay, so now, so that's it. There are no like terms to add or subtract, unfortunately. We're done. So let's see what the difference quotient is. copy the entire thing because that is your f of x plus h, and now minus the original f of x, which is x squared minus 2x plus 3, divided by h. This is where you get rid of the parentheses, so you're going to have negative x squared and positive x squared. They're gone. Negative x, 2x and positive 2x, and then positive 3 and negative 3. Remember that that minus in front of parentheses changes all the signs inside. So they all cancel. And you are left with 2hx plus h squared over h. Is there any way to simplify this? We do what? Take out the h. Very good. So h, 2x plus h over h. Anything else? Cancel h's. And there is our answer. 2x plus h. It is a procedure. It takes some time for this to sink in. But once you get it, it should be a routine. And really, the entire thing will just depend on your algebra knowledge. How well you operate with these terms, moving them left, right, so on. Yes. So since we are done, but I still want to tell you what this is. I'm not going to put it on the notes because it's not part of this course. But there are three basic concepts of calculus: limits, derivatives, and integrals. This difference quotient combined with the limit is a derivative, which is the most important part of calculus 1. Yes?
Did we miss a part like that negative 2h? Is that just cancelled?
Oh, yeah. The 2h.
Yeah.
Yeah, I should write it. I'll write it in. So as you can see, there's your difference quotient. As we learned it in class, you put this in front of it, and you get the definition for the derivative. And that's going to be your calculus 1. So don't kind of put things aside. Even though we don't have any kind of rhyme and reason for doing this in class other than you practicing the skill, in Calc 1, this is coming back in major way. The most important concept of Calculus 1 will be this formula that you're learning today. And obviously calculations regarding that formula. So make sure you don't miss that. Now I did miss this term as I copied everything. See it there? Minus 2h. So I have to add that term in my calculations here. Minus 2h. And that will add minus 2 over here. And it will add minus 2 in the answer. Hence, it's when you are looking at the calculus, h goes to 0, that will go away, and you will have 2x minus 2, and that will be the derivative of the function that we had. So it was x squared minus 2x plus 3. The derivative of that is 2x minus 2. So that's the way to compute derivatives, actually. And that ends 1.3. Going to take a short break, about 17 seconds, and then we'll restart the stream for a review on 1.4 and see how far we can get.